Welcome to another video lecture. Let's take a couple of examples to understand the block diagram reduction method to calculate the transfer function in control system. So in the first example, let us take blocks connected in series and parallel. So suppose there are blocks connected like this, the gain G1, G2, a block G3, and these are connected like this. Another block G4, and these blocks are added with the summing element. Both are added, and this is connected by a feedback network like this, and the input is given to this terminal. This is subtracted here. This is the takeoff point here, and finally we are getting output at this point. So the question is calculate transfer function using block diagram reduction. Block diagram reduction. So how to calculate the overall transfer function? By reducing the blocks by reduction rules, which we have discussed in the previous lecture. So one by one we will reduce the blocks, like these two blocks G3 and G4 are added by the summing element. First of all, if the summing element is connected after the block, then it will act as a parallel. These blocks will act as a parallel blocks. And if the summing elements are connected before the blocks, like this summing element here is connected before these blocks G1 and G2, so this will act as a feedback block. So we will apply the rule of closed loop transfer function here. But this summing element, which is connected after the block G4 and G3, so now since the summing element is connected after the block, these G3 and G4 are in parallel. So and similarly we can clearly see that this G1 and G2 are connected in series. So we will apply the series rule here, and G4 and G3 are connected in parallel. So we will apply the parallel rule here. So the equivalent diagram I'm directly writing here. So the equivalent diagram will be like this. This is the input signal. Since both the G1 and G2 are in series, so I'm writing the equivalent G1 G2 representing by single block, and these two G3 and G4 are in parallel, so I am writing here as G3 plus G4, both will be added. This is the output terminal, and there is a takeoff point here, and the signal goes again to the input with the feedback network here. Now, so this is the equivalent diagram. I have represented these two G1 and G2 with the single block with again G1 G2, and these two G3 and G4, these are added G3 and G4. Now there is a feedback, if you can remember. I have represented the closed loop control system. If you can remember, a closed loop control system like this, with the feedback gain H. It can be represented by a single block with the gain G upon 1 plus GH, if there is a negative sign here. So it will be G upon 1 plus GH. Now since there is no feedback gain given to this, so in this case the gain will be unity. So if there is no gain, there will be unity gain. So we can represent this feedback, closed loop feedback, by a single block with the gain G upon 1 plus GH. So I am further reducing this block diagram with the gain. In this case, the value of G is G1 G2. So it will be G1 G2 divided by 1 plus GH. So the value of G is G1 G2, and the value of H is 1. So in this case, the value is 1 multiplied by 1, and after this we have G3 plus G4, G3 plus G4, and finally the output C. Now these two blocks are in series, so both the gains will be multiplied. So the finally I can write it as I can represent it with a single block with the gain G1, G2 multiplied by G3 plus G4, since both the blocks are in series, divided by 1 plus G1, G2. So the transfer function of this complete block is C by R, which is the output divided by input, equals to G1, G2, G3 plus G4 divided by 1 plus G1, G2. Okay, so I think you got this. Let's take another example of this block diagram reduction technique. This is example number 2. So in this block diagram, we can not clearly predict whether the blocks are connected in series or parallel, like this G2 and G3 are not in series. There is no clear feedback with the G2 and H2, and similarly there is no clear feedback with this block G1, G2 and H1. There is a summing element in between. So we have to shift either takeoff point or the summing element before or after the block to clearly either apply the rule of series or parallel or the feedback connections. So here we can see this takeoff point here, it can be shifted. If it can be shifted at this point, output terminal, if we can able to shift this takeoff point at this point, then we can apply the series rule with G2, G3, and then we can also apply the feedback rule with this H2 also. So by simply shifting this takeoff point, let us assume that this takeoff point is A. If we can shift this takeoff point from position A to position let it be output terminal C, then we can solve this further. So I am just removing this takeoff point from this point. Let us remove this takeoff point from this point, and then shift this takeoff point from this terminal to this terminal. So I'm connecting this takeoff point from this terminal to this terminal. But as you can recall, the shifting of takeoff point, let me write it here. The rule for shifting takeoff point after the block, if you can recall that rule. So we have suppose signal X is given to a block with the gain G1, the output is XG1, and we have a takeoff point at this point. The value of that takeoff point was X, and we have shifted this takeoff point to this point. Then the equivalent diagram in that case was G1. At this position the gain is XG1, but we want it to be X. So what will be the value? We need to divide this with the gain G1. 1 upon G1, we will multiply by 1 upon G1 so that we can get the exact value X. So the rule is, if we shift this takeoff point after this block G3, the signal will be divided by this gain G3. So when you shift this takeoff point from this terminal to this terminal, this gain H1 will be divided by G3. So let me erase this and again write the actual value here. After the shifting, the value will be H1 divided by G1. Okay, so this will be the change after this shifting of takeoff point. Now we can clearly see here that G2, G3 are in series, and this will be can be represented by a single block. So let me also erase this, and I can represent it with the single block G1, G3. Okay, so let me again redraw this, and this again here I can represent it with a single block G2, G3, and because both the blocks are in series. Now this there is a feedback network with the G2, G3 and H2. We can apply the feedback rule, which I already discussed in the previous example also. So let me redraw this block diagram again with the applied reduction rules. So this is the input signal. There is again G1, and there is a summing element here. Now we can remove the summing element, since we have applied the feedback or a closed loop control system reduction method. So we can remove this, and we can represent this with a single block. We can represent these with a single block with the gain. So if you can remember, the overall gain of the feedback network is 1 upon 1 plus gh if there is a negative sign there. So it will be g upon 1 plus gh. The value of g here is g1, g2, and value of h here is h2. So it can be represented by a single block with the gain g2, it will be g2, g3, it will be g2, g3. So it will be g2, g3 divided by 1 plus g2, g3, h2. It is represented by a single. And there will be feedback network with the gain after applied shifting of takeoff point. The gain will be h1 by g1, and there is a takeoff point from where the feedback is taken, and this is the output. Now clearly these two blocks g1 and this one is in series, so we can multiply the gain of these two blocks and can replace with the single block, and these two blocks are in feedback with this h1 by g1. So the equivalent diagram here, I can let me again redraw this. Remember, you need to redraw again and again after applying the reduction rules in order to get the final transfer function. So let me again redraw this. The overall gain in this case is g1, g2, g3 divided by 1 plus g2, g3, g2, g3, h2, and in the feedback we have h1 by g1 is a feedback. This is the input signal, this is the output signal. Now we can simply apply the closed loop reduction method in this, where this is the gain g and this is the feedback h. So I am simply writing here the overall transfer function c by r equals to, this is g, g1, g2. So g is g1, g2, g3 divided by 1 plus g2, g3, h2 divided by 1 plus gh. So this is the value g, g1, g2, g3 divided by 1 plus g2, g3, h2 into h. H is h1 by g1. So we can further simplify this and can calculate the transfer function. So I hope you understand this block diagram reduction method by these two examples. Thank you.